Awesome. Thank you all for logging in today. Like Circe said, I'm going to be talking about controls on estuarine sediment bed erodibility. So to start off, what is sediment bed erodibility? Well, it's how susceptible sediment is to being picked up off the sediment bed in response to the movement of the overlying water. And I also wanted to start off with my 6-word story. It's a little bit of a spoiler for the end of my presentation, but my 6-word story for my presentation is erodibility is mostly driven by hydrodynamics. So why do we care about erodibility? Well, I think everyone should care about erodibility. It's been the last 3 years of my studies here at VIMS, but there are both ecological and societal impacts relating to erodibility, the first being benthic community structure. So throughout the York River, there are a lot of different types of sediments. We see more sandier sediments along the coastline and out at the mouth of the river by Goodwin Island. And then we see some more muddier sediments in the deeper channels. So with these different types of sediments, they can govern which type of organisms settle and live there, but also only certain organisms can survive in highly erodible areas. But in turn, organisms can also affect the erodibility of sediment in various ways by either tube building or through sediment pelletization. Next, there is concerns with light attenuation. So in areas with increased erodibility, it also increases the turbidity of the water, like the left-hand side of this figure here. So when the water is really turbid, that sunlight isn't allowed to reach deep through the water column, causing issues for the primary producers in the system, including both phytoplankton and seagrasses, which are really important organisms in estuarine systems, as opposed to the right-hand side of the figure where the water is a bit clearer and there are more phytoplankton and more seagrasses. And societal impact having to do with erodibility is channel dredging. So a lot of the deep navigational channels in Chesapeake Bay have to be dredged for the safe passage of large ships. And in this navigational chart here, the red line represents the channel that is dredged, and the is the place that all of that dredge material is kind of dumped into. So in this figure, it looks like they're in very close proximity to each other, but sediment erodibility is taken into account when determining these best placement strategies for the dredge material. So my study objectives are to determine what sediment and water column properties are driving sediment erodibility. I want to know what's making it more erodible or less erodible in the York River. So what do we already know? Well, we know that erodibility varies both spatially and temporally in a lot of different areas, including the York River, from past studies. And we also know some relationships from the literature as well. So we see that as sediment increases in bulk density, which is a kind of a measurement of how firm the sediment bed is and how much water there is in the sediment. With an increase in bulk density, there tends to be a decrease in sediment erodibility. With sand, as we see higher percent sands in the sediment samples, we tend to see a decrease in erodibility due to those larger sands just being harder to pick up off the bottom than the smaller size grains. However, we also see a decrease in erodibility with the percent clay in sediment. So clay particles actually have a magnetic charge associated with them. So the more clay that there is in a sample, it tends to make the sediment more cohesive. And that cohesive property makes that sediment much harder to erode. And then lastly, relation to tidal range. So it's been shown that there has been higher erodibility after times of a spring tide, so during higher tidal ranges or larger tidal ranges, and this is due to higher bed stresses kind of chewing up that surface sediment and allowing it to be easily eroded thereafter. So how I answered my question, I used an extensive data set that was collected in the York River. Each of these red dots is one of our samples. There are over 150 sample cores that were collected over the past 15 years. The samples all have values for sediment erodibility, grain size distribution, organic content, and distance upriver. And then we also acquired data for surface salinity, which is related to river discharge. And This is important because during times of high river discharge in the York River, the estuarine turbidity maximum, which usually is up around the West Point area, moves up and down the river depending on river discharge. And at times of high river discharge, there's actually a secondary turbidity maximum, or STM, that is present in these in this area of the river. So we wanted to see if the presence of the secondary turbidity maximum was affecting erodibility. We also have data for tidal heights to see if that spring neap cycle is affecting erodibility. We ended up squaring these data because tidal height squared is on the range of shear stress, bottom shear stress related to the tidal cycles. And then last, we have water level anomaly, which was just the absolute difference between the observed tidal range and the predicted tidal range. And this was to see if large wind events or storm events were causing an increase in erodibility. So I'm going to show you 3 different data subsets today. The first one is the estuarine subset, which includes all 150 samples taken throughout the river. The next is the Claybank and Gloucester Point subset, which are boxed here. And these were used in previous studies kind of as 2 endpoints in terms of hydrodynamic and physical sediment properties. And also these 2 sites were had the highest number of samples in consistent locations in our data set. So I combined these 2. And then our last site is the Claybank site. And as you can see, it has over 2/3 of our sediment samples. So this is the 3rd data subset that I'll present today. So a little bit about this data set. It's very extensive, and I'm very excited to be working with it. It started in 2006 with a past member of my lab, Pat Dickett, who started to look at sediment erodibility in the York River and really try to determine what was driving erodibility. And then down here, we have one of my advisors, Grace Massey, slicing some sediment out on the boat. In 2011, the same thing was going on, a continuation of that study. We're using the same box core, same. In 2016, I was actually an REU student. This is me right here in our lab, and I had a hand in collecting some of the samples that's in this data set. And at the time, I had no idea that it would be a huge part of my master's research. And then fast forward to 2019, again, slicing on the boat, the same methodology. So this is a really great data set to help me answer that question. So to look at relationships between kind of what's driving erodibility, we can look at simple linear regression. And so on the x-axis of these figures here are what are called explanatory variables. So this is the percent sand, bulk density, tidal range, those properties that I introduced earlier. And then on the y-axis, we have erodibility. So this is the parameter that we're trying to predict. So that's like my big question is what's affecting erodibility. So we're able to look at these individual relationships between the explanatory variables, again, on the x-axis, and look at how they relate to erodibility with a simple trend line, which you see in red. However, I use multiple linear regression, which allows us to look at each of the explanatory variables and how they influence erodibility, but it takes into account the other relationships. So all of my data was standardized with a mean of 0 and a standard deviation of 1 prior to model formulation. Therefore, the beta values, or simply the slopes of these red lines, can be directly compared between explanatory variables within the model. So essentially what that means is a steeper slope, either in the positive or negative direction, is a larger absolute beta value and is therefore more influential on erodibility. So then within each data subset, the Estuarine, Claybank, and Gloucester Point and Claybank subsets, the beta values for the top performing models in each subset were averaged. And that is what this figure is showing here. So to walk you through this, along the x-axis, we have those explanatory variables, the ones we think are playing a part in how erodible the sediment is. And on the y-axis, we have absolute beta values. And then these signs here show whether there was a direct relationship between the explanatory variable and erodibility, or an inverse relationship between the explanatory variable and erodibility. And then the different colors represent by different data subsets, the darkest being the smallest data subset at Claybank, and then the medium color being Claybank and Gloucester Point, and the lightest being the entire estuary. So for tidal range squared, we saw a direct relationship where higher tidal ranges led to higher erodibility thereafter. So that's what we expected to see, and that's what we found. And these beta values increase as spatial variation decreases, meaning that as these data subsets get smaller and smaller, this beta value grows and is able to predict erodibility more accurately. Next, we have salinity and percent organic. And again, these are related to that river discharge causing low salinity during times when the STM is likely present. So that inverse relationship with salinity, we see increased erodibility during the time when the STM is present. And then when the STM is present, it has the ability to trap fine-grained sediments. And these sediments are able to stick together and deposit, and they tend to have a really high organic matter. So that's what's driving this positive relationship of organic matter and erodibility. And again, these two parameters are kind of tracers of when the secondary turbidity maximum is present in the lower reaches of the York. And then we have percent clay of the sediment. So we saw a greater amounts of clay tends to lead to a decreased erosion, which again is because of that greater cohesion between the clay particles and the sediment really sticking together and being difficult to erode. Next is water level anomaly. So we saw a direct relationship here with an increased water level anomaly resulting in increased erodibility. And that just goes to show that greater winds and storm activity are likely adding to that disturbance of surface sediments and making them easier to erode thereafter. Distance up the river, it was only used in the estuarine site because the other two data subsets were just one or two locations, but this relationship is likely due to the really sandy sites down at the mouth of the river being one endpoint and the very muddy clay bank being another end member of the data set. So we tended to see an increase in erodibility as distance up the river increased. And then lastly, we have sand. We saw an inverse relationship with sand, where an increase of sand grains tended to decrease erodibility, and that's due to that increased critical stress of those sand-sized grains. So what does this mean? Well, we saw that the hydrodynamic properties were driving erodibility more than, influencing erodibility more than the sediment property. So that included the tidal range squared and the salinity being having those steepest slopes in our model. But our relationships also suggest that deposition and recent bed disturbance, these properties that are boxed here, are leading to a higher erodibility, and cohesion and consolidation, which are these parameters here, tend to lead to a lower erodibility, which again brings me back to my 6-word story. Erodibility is mostly driven by hydrodynamics. And with that, I would like to thank my funding sources, VIMS, CERDUP, and NSF, and my advisors, Dr. Carl Friedrichs and Dr. Grace Massey, and everyone in the CHSD lab that had a hand in collecting this data set to make me, allow me to answer this question. And with that, I will take any questions from you.